How's it going, everyone? So recently when Donald Trump appeared on the Joe Rogan podcast, at one point the two men started discussing nuclear energy. And in that discussion, they discussed wind farms, fossil fuels, and the energy grid in general. And I thought I'd give a brief technical background of that subject matter so people can understand that and their discussion around it better. And it's quite fitting timing because last week was Nuclear Science Week, which is a week to encourage education on nuclear science. So let's get into it. Now, if we're going to be talking about the energy grid, it's good to first discuss, well, what is energy? And there's different levels at which we can answer that question. On the most technical level, the energy converted in a process is the integral of force over a path along which that force is applied onto an object. And to put that in more approximate, simpler terms, if you're applying a force onto an object to move it along a certain path, if you take the force applied along that path and multiply it by the length of the path, you get the amount of energy converted in that process. Now, sometimes people talk about energy production. Sometimes they say power or power production. Sometimes they'll use these terms interchangeably. There is a technical difference. Power is energy used over time, or energy converted over time, energy spent over time. So you can think about a certain amount of energy produced, or you can think about a certain power production, right? So amount of energy produced over time. So you do hear both of these terms when people are talking about producing electricity. A more simple way to think about it is, let's say you have a pot with water and it's boiling. And let's say you have the same pot with the same amount of water, but it's not boiling. Well, the boiling pot possesses something that the other pot does not. Okay, and that something is energy. And how I like to describe it is that energy is what animates the mass in the universe. Now, it can take on different forms, and we can convert it from one form to another. And what's especially convenient about that is that electricity is a very convenient way to transport energy. So you can convert energy into electrical energy, transport it to another place, and then convert it back into the energy you want. Now, before we get into the details of how to do that, we also want to make note of mass. So what Einstein showed us with his famous equation E equals mc squared is that mass and energy are also the same thing, just different forms of it. So mass itself is also just a different form of energy in a way. If you take a piece of mass, multiply it by the speed of light squared, you get the amount of energy that that mass is equivalent to. And that's actually how nuclear reactions work. They take mass and convert it into energy. And because the speed of light is such a high number, and speed of light squared is an even bigger number, well then a small amount of mass gets you a huge amount of energy. So, for example, you can use a fossil fuel plant or a nuclear plant to use thermal energy, convert it into electricity, transport that electricity to your house, and then plug in, say, a speaker into your wall, and then that energy is converted back into kinetic energy, because that's how your speaker works. Okay, or you have a wind farm or a hydroelectric plant. Well, they take kinetic energy, which is the energy of motion, and convert that to electricity, which is then transferred to someone's house, and then there it's converted into whatever the person wants. Solar panels work differently. So they're actually made out of a crystal which releases an electrical current if you shine a light onto it, and that's how they generate electricity. So there's different ways to do it. Now, in a lot of power plants, you have a spinning part. Okay, so in wind farms, well, you can see it spin right there. Right? In hydroelectric plants, water is spinning a turbine. In thermal power plants like fossil fuel plants, nuclear plants, you have steam that's turning a turbine. So here's why. There's a natural phenomena, and I won't get into all the details of how to design a generator. I could do that in a different video, but roughly speaking, if you have a magnetic field and you change the velocity of a conducting material within that magnetic field, then you get a current moving through that conducting material. And you can design a specific correct shape of a conductor such that if you spin it in a magnetic field, then it'll generate electricity. And then the question just turns into, how do you make it spin? Okay, well, a thermal power plant uses steam to rotate a turbine, which is connected to a contraption that looks something like this, and that generates electricity. So the question then is, how do you create the steam? Well, by boiling water. How do you boil the water? Well, if you use it, if you burn coal to boil the water, that's a coal power plant. If you burn gas, that's a gas power plant. If you if you use a nuclear reaction, that's a nuclear power plant. Okay? If you're not using steam, right, you're just spinning it directly using water or wind, well, that's a wind farm or a hydroelectric plant. So you have many different energy sources, and a lot of the time they're separated into those that emit gases as part of the energy production process and those that do not, right? So the emitting sources, we have biomass, which includes something as simple as burning wood. We have fossil fuels, which is natural gas, coal, petroleum. And we have non-emitting sources, solar, wind, nuclear, hydro. Now, all energy production methods do produce waste. Now, people think of renewables as something that doesn't produce waste, right? People think, oh, solar, wind, hydro, that's just, there's no fuel involved. It's just the sunshine and the flowing water and the wind. Well, in that part, there's no fuel involved, but you still have to manufacture the materials. And the materials wear down. You still have to dispose of the materials. So there's still waste involved. So people are very familiar with greenhouse gases as waste produced in fossil fuel plants. People are aware of spent fuel as the waste produced in nuclear power plants. But look at the two bottom pictures here. Okay, the bottom left and the bottom center, you have solar panels that are already worn out. They can't be used anymore. They need to be disposed of. In the middle at the bottom, you have pieces of wind turbines that are worn out, used up. They can't be used anymore. They need to be disposed of. And in their discussion, they actually mention this. They mention needing to dispose wind turbines after they've been used for too long, right? This is the case for many materials in industry, right? They have a certain lifetime, and then you have to dispose of them. So they also mention birds being harmed by wind turbines. So this is one of the issues with this particular power production method. It's not just birds. Birds and bats and insects do get killed by wind turbines. It's not just crashing into the turbines that can harm these creatures, but the turbines create pressure changes as well. These are quite drastic pressure changes for the lungs of birds and bats, and that can also harm these creatures. So deaths can occur from that as well, not just from crashing into the turbines. Now, there are ways that this can be mitigated for, or people try to mitigate for it. For example, where the wind turbines are built, when they're operated, so they're not operated when birds are migrating, for example. These are methods that can reduce the harm to birds, but these methods do have limitations. So for example, you do want to build wind turbines where there is stronger wind. Well, that's also where it's easier for birds to soar. Also, rodents can hide underneath the bases of wind turbines, which attracts certain birds that hunt them. So there are limitations to these methods to reduce harm to birds, and it is a subject which is debated. So on one side of the debate, you have people saying that, well, by far the biggest threat to birds isn't wind turbines, it's cats. And after cats, it's actually buildings. And so when you take that into account, wind turbines actually make up a very small portion of bird deaths. But the counter argument to that is, well, cats and buildings aren't going anywhere, whereas deaths from wind turbines is something that could be prevented, for example, by using other energy production methods. So why not prevent the harm that could be prevented? So this is something that is an issue, and it's something that is debated. When it comes to bats and insects, well, when you're dealing with insect deaths, you're dealing with how that affects pollination and plant growth. So that's also a factor that comes into the discussion. With bats, it gets kind of complicated because bats eat a lot of insects. So on one hand, you have wind turbines killing insects. On the other hand, you have them killing bats, which may increase the population of specific types of insects, specifically the ones that are easy for bats to catch at night. So it alters how much of what types of insects there are, which alters which plants get pollinated, and has these kind of complex effects which people are studying and looking into. Now, in terms of efficiency, and this is how their whole discussion starts, right? Joe Rogan starts talking about how great nuclear energy is. It's absolutely true that nuclear is by far the most efficient. So here we can look at the amount of fuel needed to power a light bulb for a year. So for coal power, and now these are all average numbers, you need about 714 pounds of coal. Now, compare that to nuclear, where you need 0.035 pounds of fuel. That's a much, much smaller number. And that goes back to Einstein's equation, E equals mc squared. With a small amount of mass, you get a tremendous amount of energy. Now, look at natural gas here, 143 pounds. Now, of course, that's much more than the mass for nuclear fuel, but it's also much less than the mass for coal. Now, people often lump coal and natural gas together as fossil fuels, but they are quite different, and you can see that just looking at these numbers. Natural gas is much more efficient at producing energy, and it's significantly cleaner than coal as well. So it is important to view these two energy production methods as different, even though they are both fossil fuels and they do both emit greenhouse gases. Now, for wind and hydro, it's about 2 hours and 30 minutes of operation to produce the amount of energy needed to power a light bulb for a year. And for solar, assuming you have 100 squared meters of solar panels, it would take 9 days. Now, if nuclear is so great, okay, if it's so incredibly efficient, and it doesn't release greenhouse gases when producing energy, then, well, why not use nuclear for everything? Well, there are a few reasons. Now, the reasons discussed on the podcast is they talk about people's concern because of a handful of nuclear accidents that were very significant accidents, and it makes people nervous about nuclear energy. They mentioned the difficulty of building very large nuclear power plants. But there is another reason, which is which is that energy demand fluctuates. Okay, throughout the day, people need more in the daytime, less in the nighttime. And so energy production also needs to fluctuate. We don't really have technology that is sufficiently capable of storing large amounts of energy. Okay, our battery technology just is not that advanced. So we need to fluctuate our energy production in order to meet the fluctuating energy demand. Okay, now here's some terms. The minimum amount of energy that needs to be produced throughout all these fluctuations is called the base load. And the maximum amount of energy that needs to be produced is called the peak. And you have energy demand fluctuating between the base load and the peak. And so the supply needs to fluctuate like that as well. Now, nuclear energy production it can't fluctuate. The plant is designed, or the reactor is designed to produce a certain amount of power, and that's it. That's how much it can produce. You can't fluctuate it higher or lower. So if you're using nuclear energy, you still need some other form of energy production to cover those fluctuations. Okay, now here's a chart of different forms of energy production and what they're capable of. Okay, now in the first column we have what is called renewable, hydro, wind, and solar. And renewable is kind of a misleading term, because when people think renewable, they think, oh, it doesn't emit greenhouse gases, or, oh, it doesn't produce any waste. And that's just not true. Okay, like we said, everything produces waste because everything needs to be manufactured and then disposed of, even if it doesn't release greenhouse gases during operation. As for release of greenhouse gases, well, nuclear also does not release greenhouse gases when operating, and we see that in the second column here. Okay, hydro, wind, solar, and nuclear, they do not release greenhouse gases for the purpose of producing energy. Renewable means that you're not using any fuel because the fuel is just the wind blowing, the sun shining, and the water flowing. Well, that's kind of misleading because you are still using fuel to produce the components for these energy production methods and to dispose of the components once they're used up. Now, the next three columns, okay, these are the ones that really talk about how practical it is to use something. And look at that middle column, fluctuation of power output. Everything on the list can fluctuate its power output except for nuclear. Okay, so nuclear, it's very, very efficient. It doesn't release greenhouse gases, right? You saw up here how efficient it is. Okay, by far the most efficient power production method we have, but it doesn't fluctuate its power output, and that's why it has to be used alongside other power production methods. Now the next column, also very important, geography and time independent. In other words, can it be used anywhere, anytime? And that's true for coal, natural gas, and nuclear. Okay, for hydro, you need the rivers for it. You need the water supply for it. For wind and solar, it depends on the weather, it depends on the time of day, and how much sunlight do you get based on your geography, how much wind do you get based on your geography. So it's not something available to everybody all the time, whereas coal, gas, and nuclear is. And is it suitable for baseload? Okay, so can it reliably produce enough power to satisfy the baseload? And so the fossil fuels, coal and natural gas can, nuclear can, hydro can as well, again, if you have the geography for it. Okay, so for the energy grid, you need check marks in all three of those boxes. You have to fluctuate power output, and you have to have enough power output for baseload, and you have to be geography and time independent, right? You have to be able to use it anytime, anywhere. All right. Now, if geographically you're lucky enough that you can use hydropower for all of these, then good, right? Hydropower can fluctuate energy output and it's suitable for baseload. But if you don't have that geography, well then you need all three of those boxes checked. And coal here is highlighted, okay? Because coal is much, much easier to find than natural gas. All right. So coal and natural gas, these are the only two on the list that have check marks in all three boxes. So there's a reason people keep using fossil fuels despite the greenhouse gas emissions. It's very, very convenient, especially coal, because coal is very, very easy to find. Okay. So that's the world that we're living in, and that's why you keep seeing fossil fuels used so much. So how would an ideal electrical grid look? Well, you have nuclear satisfying your baseload, and then for the fluctuations you use other renewables where possible, depending on the weather, how much of them can you get per day. You use those to reach your peak, to get as close to your peak as possible, and then for whatever's missing, then you use fossil fuels to make up what's missing, right? And that's the convenient part about fossil fuel plants. You just turn them on and off, produce as much energy that you need when you need it, and turn it off when you don't need it. right? So nuclear for the base load, other renewables as much as you can to reach the peak, and if you still haven't reached the peak with nuclear and other renewables, then you use fossil fuels to make up for what's missing there. That would be the ideal case. Okay, now here's an image of power production in Germany. On the left we have 2012, on the right we have 2020. Okay, so we have in 2012 for the base load, we have some hydro, some nuclear, and a lot of coal and gas, right? And then we have some renewables on top of that. Mostly we see wind and solar there. And then in 2020, by that point, there were some energy reforms done in Germany, and now you see there's no nuclear. And you have, so a lot of conventional energy production, but you have a lot more solar used, right? So if you see these big yellow peaks that actually dip down, right? So when solar can produce a lot of energy, that's used for as much as possible. And you also have wind, you have biomass, you have some hydro there as well. Okay, now imagine that nuclear was used as much as possible in these situations. Okay, well then nuclear would satisfy your base load. So you would produce nuclear to meet that minimum amount in both cases. And then you have, a much less that you have to make up. And the other renewables can make up pretty much all of it. Okay, and then we're closer to this ideal situation that we see on this slide here. Okay, now when they discuss nuclear, they discuss the difficulty of building it. They talk about concrete a lot, and they talk about some nuclear accidents which make people nervous about nuclear. Now, I'm not going to get into the design of different types of nuclear power plants. That could be a whole other presentation, and if you're interested, let me know in the comments. I can make a presentation on that as well. But generally speaking, in all thermal power plants, you have water coming in and water coming out. Let me get a pointer here. Okay, so you have, water coming in and steam coming out because that water is heated up. Okay, now this type of nuclear power plant, it's used a lot in the United States. It's called the BWR, or boiling water reactor. Your nuclear reaction heats up, boils your water, and you have steam coming out. Steam turns the turbine. Okay, now here's another type of design on the left here, also used a lot in the United States. You have water coming in, steam coming out, but what heats up the water is not the nuclear reaction, but a different loop with hot water. And how does that other water become hot? By going through where there's a nuclear reaction. On the right side, we have a power plant design which is used a lot in Canada. Again, look, water coming in, steam coming out. And how is that water heated up? By a different loop of water, which is heated up using a nuclear reaction, but the reactor is designed differently. Okay, now always around these mechanisms, and this is like the size of a multi-story large structure, you have these concrete casings. Okay, so here you have a photograph of a nuclear power plant. You have a diagram how it works. This plant actually has 4 reactors, 1, 2, 3, 4. Okay, and inside, look what you have here. You have your reactor where the water heats up. Okay, you have it heating up a different loop of water where you have water coming in, steam coming out. This part is called the steam generator. It's inside this dome of concrete. Okay, now a big purpose that serves is to stop radiation from exiting the structure. Okay, here's another diagram, same idea. Here's your nuclear reactor. Here's your steam generator, water coming in, steam coming out, and later that steam exits and rotates the turbine, which generates electricity, and it goes to your power grid. Right, actually up here you see that as well. There's your steam turbine, electrical generator, and that goes to your power grid. Just for size comparison, this face right here, so this is the can-do design of nuclear reactor, used a lot in Canada and some other countries. This face here, that's this part right here. Okay, this edge here looks like this. So you can see the height of a person, so you can get an idea of what things look like. Now even this diagram is not to scale. Here it's a little bit more to scale. Okay, here's the face right here. That it's called the calandria face. Okay, that's this section right here. Okay, this is where nuclear fuel bundles are inserted into these openings here. And these blue long structures, these are the steam generators. And here you have your concrete vault all around. Okay, now that concrete, and it's used within as well, okay, it plays a very important role of blocking radiation. Okay, so what is radiation? Well, a lot of people think radiation, they think electromagnetic radiation, which we're most familiar with in terms of visible light. Okay, so this is, for lack of a better word, it's a type of wave that just exists in nature, a type of waves that exist in nature called electromagnetic radiation, and they have different wavelengths. And the wavelengths we can see range from red to violet. Okay, so the larger wavelengths look more red to us, and the smaller wavelengths look more violet to us. Now, wavelengths that are even larger than red, our eye can't detect them, but we still use them. These are called infrared and microwaves and radio waves, which we use for communication. Okay, like our cell phones, right? Use radio waves, internet, radio waves. Now, once wavelengths get smaller than violet, our eyes can't detect them, but we do still interact with them. These are ultraviolet rays, X-rays, and gamma rays. Now, once those wavelengths get smaller, that's when they can get more harmful. So ultraviolet rays, well, that's why you need protection from the sun, to protect yourself from ultraviolet rays. X-rays, that's why there's limits of how much X-rays you can get per year. That's why you wear protection when you get an X-ray. And even smaller wavelengths than that, these are called gamma rays. And nuclear reactions, you get gamma rays coming out too, and you need that concrete to block it. But you also have other forms of radiation called particle radiation. Alpha radiation is 2 protons and 2 neutrons flying through the air. Beta radiation is an electron flying through the air, and these are easier to stop than gamma rays. But you also have neutron radiation. Now, neutrons, they don't have a charge. Right? Protons are positively charged, electrons are negatively charged, so as they fly through the air, they might curve and bend towards something that attracts them or away from something that repels them. But neutrons, because they're neutral, they'll just fly straight for a long, long time. And that's what makes neutron radiation more harmful as well, and concrete is used to stop that too. Okay? Now, radiation is a natural part of the world around us. As an analogy, it's kind of like microbial life, germs. It's a natural part of the world around us, right? We're interacting with the sun all the time. There's objects, just like everyday industrial household objects, which also emit radiation that our eyes can't detect. It's just a natural part of the world around us, but if we get too much of the harmful type without using protection for a long period of time, well, that's when you can get hurt. For example, ultraviolet rays from the sun. Or if you get a very large dose of radiation in a short period of time that your body can't handle it, that can be harmful as well. Just like being around germs, right? You're always interacting with them, but if you're interacting with too many of them over a long period of time without proper protection, that can cause problems. Or if you get a very large dose of them in a short period of time, your body can't handle it and you can get problems from that. Okay? So here's a comparison. You have 2 photographs. Which place do you think has a higher yearly dose of radiation, right? And intuitively think, well, the picture on the right, which is actually a photograph from the exclusion zone at the Chernobyl site. But the answer is the photo on the left, which is a beach in Brazil. It actually gets more radiation per year, at least today, right? So that just goes to show that it is something that's around us all the time, and it's not something that only exists where a nuclear reaction is occurring. Now, one of the things they mention in their conversation is nuclear disasters that have made people nervous about nuclear. They mention Chernobyl, they mention Fukushima, and they mention 3 Mile Island. Now, 3 Mile Island was a much smaller scale event than Fukushima and Chernobyl, so it really should be in a separate category. It shouldn't be viewed as being at the same level as Chernobyl and Fukushima. Fukushima is unique as well because it was actually a very large-scale natural disaster, and the nuclear power plant was affected by that natural disaster, and you had the events unfold as they did. Chernobyl was just a nuclear disaster. And one of the things that Joe Rogan mentions is that, well, they build them differently now. The case for Chernobyl is actually, they were already building them differently back then. Chernobyl, when it existed, was already a flawed design. Power plants all over the world at that time were already built in a much safer manner than how Chernobyl was built. And one of the major issues with how Chernobyl was built is that it lacked this concrete dome. And so when you had radiation coming out at very high levels, there wasn't that concrete to stop it. Okay, when you had the initial explosion, you didn't have a concrete dome to block materials and gases from spreading upward. And even if the concrete dome breaks, which happened in Fukushima, you had structures breaking. Well, you have concrete falling down onto the reactor, and even that broken, fallen pile of concrete also creates a certain level of protection. You didn't have that at Chernobyl. Okay, so not only was Chernobyl built in a flawed manner, it was also operated in a flawed manner. And in fact, if it was operated correctly, then despite the construction flaws, the disaster would not have happened as it did. If it was operated incorrectly, but it didn't have the construction flaws, then again, the disaster would not have happened as it did. And you actually did have safety mechanisms at Chernobyl that were operating and were kicking into place as they were supposed to when the plant was being operated improperly. But because that was interfering with an experiment that people wanted to conduct, they actually shut off the safety mechanism. And then the disaster occurred. It's also important to note that the explosions that happened at Fukushima and at Chernobyl were not nuclear explosions like what you would get from a nuclear bomb. These were conventional explosions, but because they occurred in places where there was radioactive material, the explosions spread radioactive material through the air and onto the land. Also, if these explosions breach the containment structures, or in the case of Chernobyl where there was no proper containment structure to begin with, and you still have a nuclear reaction going on, well, that can also spread radiation through the area. A nuclear power plant cannot explode the way a nuclear bomb explodes. It's just a completely different technological mechanism, even though it's made out of some of the same material. As for plants being built differently, well, when a disaster happens, like at Fukushima or like at 3 Mile Island, this is the case in all industry. An accident happens and people make changes to designs to make sure these accidents don't happen again. Plants are built to withstand natural disasters, but the natural disaster that happened at Fukushima was something that people just were not prepared for and were not expecting. Okay, now later on in the discussion, so Trump mentions the rules for concrete at nuclear power plants, that there's very strict rules, and that these are very large structures that are difficult to build, but he mentions a solution. I believe what he's referring to is modular reactors or small modular reactors, because he talks about reactors that can produce less power, but they're made out of components, and you just add these components if your power demand increases. So I think he's talking about modular or small modular reactors. So rather than a reactor like like the power plants we have now, where it's basically like a massive factory, a huge campus. It's built on site. Modular reactors are built somewhere else, and then they're transported to where they are needed to produce energy. And they produce less energy than your typical power plants, but you can add more of them to produce more energy, right? As you add more of these modular reactors to a site. And you just build them where they're constructed and transport them to where they need to be used. And there is a push right now all over the world to start building small modular reactors to produce energy, just for the masses. Now, in North America, this is particularly useful in smaller remote communities, like remote northern communities, where it's difficult to connect them to the electrical grid. Now, small modular reactors are not something new. Okay? They have been used for a while on ships, on submarines. There have been ideas to use them in space and on airplanes, but people moved away from those ideas in case there's some issue. They didn't really want a nuclear reactor falling from the sky. But they are still used regularly on ships and on submarines. You have nuclear-powered ships, nuclear-powered submarines, so they can sail for a very, very long time and using very little fuel. So we already have small modular reactors. What the push is that's happening right now is to use them just for like everyday energy production rather than on vessels. So I hope that gives a good background to you about the discussion that they had. And until next time, enjoy.